Hello and welcome everyone to the week 2 of our course Secure Computation Part 2. So I will discuss first recapitulations of week 1 contents, and then I will discuss the assignments that were posted for week 1 in the NPTEL website, and then I will proceed to discuss the concepts of week 2 in brief. So let me first share my screen and then we will continue discussing. I hope my screen is visible. So okay. So we will just quickly revise the topics of week 1. So the first thing that we were introduced in the course of secure computation, where we are dealing with malicious adversaries, right? So if a party among a n party setting, if a party gets corrupted, it can behave arbitrarily and it is not bound to follow the protocol. So how to handle these kinds of adversaries when there are at most t number of corruptions are possible. So first thing, we started with our two basic protocols, which are Byzantine agreement and reliable broadcast. So if you remember, I will just quickly cover them. So in Byzantine agreement, we have n number of parties with each of them having their individual inputs. So let's say parties are P1, P2 to Pn, and they have individual inputs, say x1, x2 till xn, and among these n parties, some t number of parties can be corrupted at maximum, right? Now if these parties are running Byzantine agreement protocol, then after the protocol ends, each party will have some output, say y1, y2 till yn. And how will these outputs be? Basically, let's say in case all the honest parties are starting with same input, right? So starting of the Byzantine agreement have same input for all the parties, then at the end of the protocol all the honest parties will have that value only as the output. So let's say in this case P1, P2 till Pn, among them let's say P3 and P4 are corrupt, but rest of the parties are starting with some input x, then at the end of the protocol all these honest parties, that is all the parties except the corrupted P3 and P4, all of them will have their yi equal to x, right? So we call this property as consistency property of Byzantine agreement. So main property or main objective of the Byzantine agreement is that all the honest parties should agree upon some value, and that is what is achieved through the consistency property. However, there is another property, that is validity property. So basically validity property ensures that if all the honest parties are starting with same input, then at the end of the protocol all of them will have same output, and consistency property ensures that even if all the honest parties do not have same input at the starting of the protocol, but at the end of the protocol all of them will agree upon same output value, right? So this is what Byzantine agreement is. So and on the other hand, there is reliable broadcast protocol, where again P1 to Pn n number of parties are involved, but among them only one party, let's denote it with say pk, this is the designated sender. So one of the end parties will be the sender, and our objective is to that at the end of the broadcast protocol, all the honest party will receive same value, right? So here also validity and consistency property comes to play when the sender PK is honest. So it can be possible that the sender itself is a corrupt party. So again, at most T corruptions are possible, but it is also possible that the sender itself is corrupt. However, validity property ensures that if sender is honest, then whatever value sender sends or it is willing to send, at the end of the protocol, all the honest party will receive that value only. But if the sender is corrupt, then also at the end of the protocol, all the honest party will receive one common output, right? So as we can see that this validity and consistency property both should hold in the case of both Byzantine agreement and reliable broadcast, right? And there is another property called termination or liveness property, which simply says that both these protocol should end after a finite amount of time. They should not run infinitely, right? So that is what termination property guarantees. And we also saw that Byzantine agreement and reliable broadcast can be converted from each other. So if you are given a Byzantine agreement protocol, using that you can have your own reliable broadcast protocol. How? So basically, if you are going to achieve RB, then you must have a designated sender, right? So at the very beginning of the RB protocol, where you are going to use your Byzantine agreement protocol, at the very first step, the sender will send its value to all the parties, right, including itself. Now it can be the case that sender is honest, then it will send identical copy of the value to all the parties. Otherwise it may choose, if it is corrupt, then it may choose to send different values to different parties. Now, so once this first step is over, basically each of the party P1 to Pn has received some value from the sender. So let's denote this value received from sender by each of the party with BIs. So P1 has received B1, P2 has received B2, and Pn has received Bn. All this B1 to Bn will be same if sender is honest, otherwise they can be arbitrarily different. Once this first step is over, then we run our BA protocol that we already assumed to have in our hand with these parties and their corresponding input BIs. So P1 to Pn will treat B1 to Bn as their input to BA protocol, and they will run the BA protocol so that at the end, by the validity and consistency property of the protocol, if the sender is honest, all the honest party will agree upon a common if the sender is honest, all the honest parties will agree upon the value which was sent by the sender itself. Otherwise, if the sender is corrupt, then all the parties will output a common value. It may not be the value that they received from the sender, but it will agree upon a common value, right? So this is Byzantine agreement to reliable broadcast conversion. And here if Byzantine agreement is defined for some t less than n, then reliable broadcast will also hold for the same t less than n condition. However, on the other hand, if we have a reliable broadcast protocol and we want to achieve a Byzantine agreement protocol from that, in that case this restriction changes little bit. So if you have a reliable broadcast with some t less than n, then your Byzantine protocol must satisfy the condition t less than n by 2. So honest majority is required for achieving Byzantine agreement when you have been provided with a reliable broadcast protocol. And how this Byzantine agreement protocol work? So as you know, all the parties P1 to Pn will start with their individual inputs, say P1 to Pn, and each of them will run its own instance of RB protocol parallelly. Each of the party will run their own RB instance considering Bi to be the sent message, right? So at the end of all these parallel n instance of RB protocol, each of the party must have received some value, say P1 to Vn, from each of the parties P1 to Pn, right? Now let's denote the value received by P1 from P1 with V11, the value received by P1 from P2 with V2 superscript 1, and so on, right? Similarly, P2 receives from P1 value V1 with superscript 2, and so on. So basically, at the end of all these n parallel instance of RB protocol, each of the party have a vector of value, vector of n values with them, right? Now what they do is that they will take the majority element of these vectors and output that as the final value of RB protocol, final value of Byzantine agreement protocol that we are trying to achieve from RB protocol, right? So majority value will be the output. Now in this case you can see, since the majority is required, there only the requirement t less than n by 2 comes to picture. Okay, so that was a quick recap about Byzantine agreement and reliable broadcast. Now we had also seen in week 1 that how to design a perfectly secure Byzantine agreement protocol for the condition n greater than 3t, right? Now in the EIG or exponential information gathering protocol, all the parties usually keep a local copy of a tree data structure, and at each round of the protocol they exchange between them the information of some particular level. So all the information at a particular level of the local copy of its tree will be broadcast to all the other parties including itself, right? So if you remember, the tree structure actually has t plus 2 levels. So t is the threshold, so we usually consider n to be the total number of parties and t to be the maximum supported number of corruptions. So at max t corruptions are tolerated, and in the tree structure there are t plus 2 levels, and at each level, say k, so at level k, each node of the tree has n minus k children, right? And you can clearly see that if there are t plus 2 levels of the tree, then there are exactly t plus 1 path, and at the end of each path segment, so from the root to leaf, you will encounter a total of t plus 1 distinct parties. So t plus 1 distinct parties or party ID will be there for each path from root to node, from root to node. So to be precise, if you have n equal to 4 and t equal to 1, which certainly satisfies n greater than 3t, the tree structure is something like this. So since this is level 0, so this node has children n minus k, where k is 0. So it has 4 children, and at level k each node will have n-1 children, so all these nodes will have 3 children, and each node of the tree will be labeled or tagged with some string. So the root node we always keep the label or tag as lambda, and then onwards we have there will be two distinct parties encountered through this path, right? So we start with labeling the first level nodes, so they are 1, 2, 3, 4 the party IDs, and then for the children of 1 we have the nodes labeled with 1, 2, 1, 3 and 1, 4. 1, 1 cannot be there because distinct party ID should be there for each node label, right? Similarly for 2 the children are 2, 1, 2, 3, 2, 4 and so on. So let's not go into those details because we have already seen those things in week 1 content. And then during the EIG protocol, let's say if we are at round R, right, then each party will send the information of its local tree at level R-1 to all the parties including itself, and then they will update after receiving such information from all the n parties. They will update their nodes at level R. After receiving information about R-1th level from all the trees, each tree will update their own tree for level R, right? And then this process goes on till t+1 number of rounds, and after that, once the local copy of each party, local tree copy of each party is populated with all the values corresponding to all the nodes, then a output decision is made. So then we go in a bottom-up approach and we assign new values to the nodes. So for the leaf nodes, the new value is exactly equal to the previous values, and then onwards we assign to each node the value which is the majority value of the values of its children nodes, and then in a bottom-up approach we will get some value at the root node, and that is what will be the individual output of each party, right? Okay. Now we will take a look at the week 1 assignments. So this is the first question of week 1 assignment. Consider the EIG tree before reassignment. So before reassignment means that before you assign the new values to the node. So the tree you can see in this picture, all the values are actually the initial values after the completion of t+1 number of rounds. This is the tree structure, and after that, for the output decision making phase, you generally assign new values to each of the node considering the majority value of the children of each node. But here they are saying that the tree you can see in the picture, all the values are actually values before reassignment of new values. So consider the EIG tree below for an honest party. So the tree you are looking at here, this tree corresponds to some honest party where 4 parties P1, P2, P3 and P4 want to use the EIG protocol to achieve Byzantine agreement. What does 0 in the node labeled 4,3 mean? So here is this node with label 4,3, the last node you can see here. So the question asks that we see that the value at node labeled with 4,3 has a value 0. Now what does this actually signify? There are options given, and also there is a hint given that whose EIG tree is this. So as you know that in EIG protocol, every party gives a local copy of this EIG tree, right? So first you try to determine that the tree you are looking at, that belongs to which party, P1, P2, P3 or P4. Now how to determine that? So let's observe the tree closely. We can see here in this copy of EIG the root node value is 1. So whichever party this EIG tree belongs to has the initial input as 1. So P1, P2, P3 and P4 must have started the protocol with some bit value, right? Individual bit value. So the EIG tree we are looking at, if it belongs to Pi, then the initial bit input of Pi, let's denote it with Bi, is actually 1. Why? Because the root node is assigned the value 1. Now let's see what each of these nodes says actually. So in this tree the node with label 1 has value 1, which means the party Pi, so if party Pi has this local copy of the tree that we are looking at, then Pi has received the value 1 from party P1. That's why Pi has assigned the value 1 to the node labeled 1. Similarly, Pi must have received 0 from P2, right? Which means that P2 has told in round 1 to Pi that my root node value is 0. Similarly, Pi has received 0 from P3 and Pi has received 0 from P4 as well. Now just see this thing, that we already know that Pi is a honest party, right? That is given in the question, that this EIG tree belongs to some honest party. So among P1, P2, P3, P4, any one will be dishonest, but Pi is not that dishonest one. Pi is honest, so Pi does not lie. Now Pi has 1 at its root node value, right? So you can see here Pi has been told by everyone except P1 that their root node value is 0, which means that Pi must be equal to P1, because only P1 has claimed its root node value to be 1 in the first round, right? So P1 must be a honest party and it has correctly told Pi, that is P1 itself, that my root node value is 1. Otherwise among P2, P3, P4 they cannot be equal to Pi, because any one of them must be dishonest and other two are honest who has value 0 at their root nodes. So it is quite evident that this EIG tree actually belongs to P1 who has value 1 at the root node, and it has correctly told itself that my root node value is 1. That's why the node with label 1 has value 1. Okay, so the first part is solved, that whose EIG tree is this? This is P1's EIG tree. Now what are the options given? First option says that P4 told P1 in round 2 that P3 sent 0 to P4 in round 1. Now in the node labeled with P3, since the last party ID you can see is 3, right? That means the last communication happened on behalf of P3. That is how we design the protocol of EIG. So if I am assigning some value to my node with label 43, that means I have got some statement from P3, right? So the first two statements in the options starts with P4 telling something to P1. P1 is the party who is holding this EIG tree, but it is listening to P3 right now. When we are populating the node with label 43, that means P3 has told something to P1. not P4. So that's why first two options cannot be the right answer. Now looking at third and fourth statements. So third statement says that P3 told P1 in round 2 that P4 sent 0 to P3 in round 1. So here basically P3 is talking to P1, that is correct. So P3 is talking to P1 saying that P4 told me in round 1 that its root node value is 0. Now this makes sense, right? That is how your EIG protocol is built. That at the first round, when P4 has told P3 that its root node value is 0, then P3 should have assigned the node with level 4 the value 0, and then in the next round it declares that in the second round P3 declares to P1 that in the previous round, that is round 1, P4 had sent me value 0, right? So basically this one is the correct option. Fourth one cannot be the correct option because here it says P3 told P2, but we are looking at the EIG tree of P1. So P1 is only receiving values from various parties to populate its nodes. So there is no meaning that what P3 told P2, right? So this is P1's EIG tree, and P1 is listening to P3 when assigning value to its node with level 4-3. So this is the correct option. Okay, I hope I am clear. Okay, proceeding to the next assignment. So consider the EIG tree below for an honest party where 4 parties P1, P2, P3 and P4 want to use the EIG protocol to achieve BA. Among the 4 parties, which one is corrupt? So we need to find the liar by looking at the EIG tree construction. So let's take a look at it. So you already know, so if you notice that this is the same EIG tree as of the previous question. So we have already solved that whose EIG tree is this? It is P1 EIG tree. Now let's find out the liar. So P1 in the first round has received from P1 itself the value 1. So we are talking about round 1, right? In round 1, P1 has received value 1 from P1, value 0 from P2, value 0 from P3 by looking at this node, right? And by looking at this node, we say that P1 has received value 0 from P4. Next, in round 2, what are the statements that this node level implies? So this node level implies that P2 has told P1 that P1 in the previous round has declared its root node value to be 1. So P1 has told P2 has told P1 in round 2 that in round 1 P1 told me that its root node value is 1, which is true, right? P1 indeed has its root node value 1. That is okay. Now what is signified by this node labeled 1, 3? This means that P3 has told P1 in round 2 that P1 has told P3 in round 1 that its root node value is 0. Now here is something wrong because P1 is an honest party. So P1 must have sent its root node value 1 to everyone. Now if P3 is saying P1 in round 2 that in round 1 P1 had sent value 0 to it, so that must be a lie, because P1 being an honest party must have sent the value 1 to everyone, but P3 is claiming that it got value 0 on behalf of P1 in the previous round. So this is a lie. So that means that P3 is the corrupt party here. Okay. So this leads to a discrepancy, and so basically it is clear that P3 is the corrupt party here. I hope I am clear. Okay. Now proceeding to the next question. Again the same EIG tree is given, and it asks, consider the EIG tree before reassignment below for an honest party, where 4 parties P1, P2, P3 and P4 want to use the EIG protocol to achieve PA. What is the output of the protocol? Now simply you have been given a EIG tree after the T plus 1 round of assignment of values. Now the assignment of new values are left, so we will simply take the bottom up approach of assigning new value to the nodes. So let's take a look. For the leaf nodes, we already know that new value is equal to the old value, so these leaf nodes values will remain unchanged. Now following the majority rule, that is whatever majority value is there among the children, we will assign that value to the parent node. So looking at this node, it has children values 1, 0 and 1. 1 is the majority, so updated value will be 1. So this does not change basically. For this node, 0, 1, 0. 0 is the majority value, so 0 will be assigned the new value for this node. So this also does not change. Here the values are 0, 1 and 1. So clearly 1 is the majority value among the children nodes. So this node value should be updated to 1. It was previously 0. So this will be updated to 1. And again here all the children node has value 0. So clearly majority is 0. So the value at node 4 remains 0. Now what is the children values for this node? So it has 4 children and they have values 1, 0, 1, 0. So clearly there is no majority here. So what will be the value of this parent node? In that case we will assign some default value, right? So the answer is default value because there is no majority among the children values of the root node. So the default value will be the output of the protocol. Okay. Also the output of the protocol means the output that all the honest parties agree upon after running the BA protocol, because we do not care about the output of the corrupt parties, right? So whatever is the, since this EIG tree belongs to some honest party, whatever is the output from this EIG tree for this honest party will be the output of other honest parties as well, right? So we move forward to the next question. This question says that parties P1 to Pn want to together generate a common random value such that a corrupt party cannot guess the value beforehand with probability 1. So basically they want to reach to some agreement, right? Now what they are doing, so assume there are n greater than 3t condition applied. So if there are n parties, at most t parties can be corrupted such that 3t is less than n. Now choose the protocols among the following which can be used to generate this value. Note that the adversary is rushing, that is the adversary can see all the values sent by honest parties in a particular round before sending its values. Here this symbol denotes the concatenation operator. Okay, so there are two protocols are given in the option, which one works, or if at all any of them works to achieve whatever the parties P1 to Pn want to achieve. So let's see. So for the first protocol it says that in round 1 party 1 selects some value 1 and sends it to P2. So party 1 selects some random value V1 on its own and send that value to P2. For round 2 to n-1, each party PR receives value C from PR-1. So R is starting with the value 2. So P2 has received V1 from P1, right? So this is receives value C from PR-1. So P2 has received value V1 from P1. Now what P2 does, it selects random value V2 and then sends v1 XORed with v2 to party next party, so that is p3, and so on. So let's say there is p4, p3 sends to p4 the value v1 XOR v2 XOR v3, so on, and pn finally receives from pn minus 1. What will it receive? It basically will receive v1 XOR with till vn minus 1, right? This is what pn receives from pn minus 1. Now pn also selects some random value vn at round n and sends this value received from pn minus 1 XORed with vn to party p1. So finally the circle gets completed and pn sends to p1 the value v1 XOR v2 till vn to party p1. So p1 receives this value ideally, and then p1 reliably broadcasts this value received from pn. So this value is reliably broadcast by p1. Okay, now does this protocol work so that we get our desired scenario where at the end of the protocol all of the parties actually agree upon some common random value. Now although by looking at the last step where it says that p1 reliably broadcasts the value received from pn, basically in this scenario a corrupt party, so our objective is that a corrupt party cannot guess the value beforehand with probability 1. But here if p1 itself is corrupted, then in the final protocol only it may choose to send different values to different parties, right? And then the agreement that we want to achieve is not reached, right? In the second option, it says that in round 1 each party pi selects random value vi and reliably broadcast vi, and the output is the XOR of all these v1 to vn. Now all the parties are doing individual reliable broadcast to all the other parties. So all the honest parties must have received some v1 to vn, where for the index with honest parties the value of vi's are same. So if I denote it, if p1 has received at the end of the reliable broadcast the values like this, okay, and so on. For all the index of honest parties, right, in between, at those indexes all the honest party will have the same entry. However, the rest of the entries cannot be guaranteed because they correspond to malicious parties index. So if the final output of each party is just XOR of all these elements of individual vectors, the parity cannot be guaranteed, because although the sum of the index, that is indexes corresponding to the honest parties, have consistent value throughout all the honest parties, the XOR of all these n vectors for a single party may not match with others, right? So to get a Byzantine agreement protocol from reliable broadcast, as you know that they actually take the majority of these vectors. So the majority value in this vector are actually output, and in that case the output will be consistent, but XORing this value will not give you a consistent output because you cannot control the output of malicious party index. Okay, so basically none of the above protocol actually gives you what you want to achieve, right? Okay, so proceeding to the next question, recall the equivalence of RB and BA protocol discussed in lecture. Choose the correct options from the following. So there is a spelling mistake here. So this will be from the type. So if we have a BA protocol for 3T less than n, then we have a broadcast protocol for 3T less than n using the reduction discussed in the lecture. So just a few slides ago we saw that if we have a BA protocol, then we can achieve RB protocol. Also if we have a RB protocol, we can achieve BA protocol, however with the extra constant that T should be less than n by 2. So BA to RB conversion is does not demand any extra condition, right? So that's why this statement is correct, because this is BA to RB conversion. The second statement, if we have a BA protocol for 3T less than 2n, then we have a broadcast protocol for 3T less than 2n. This is also okay. Next statement is, if we have a broadcast protocol for 3T less than 2n, then we have a BA protocol for 3T less than 2n. Now this is the conversion from reliable broadcast to Byzantine agreement. In this case, let's check whether T less than n by 2 is satisfied. So in this condition, basically T is less than 2 by 3n. However, 2 by 3n is actually greater than n by 2, right? So if T is less than 2 by 3n, then this is not guaranteed that T is less than n by 2 also. So we cannot really comment that whether we will have a BA protocol for 3T less than 2n or not. It is possible only if T is less than n by 2, but that is not satisfied here. But the fourth option says, if we have a broadcast protocol for 3T less than n, then we have a BA protocol for 3T less than n. Now 3T less than n means n is less than T is less than n by 3, so which is clearly less than n by 2 as well. So in this case, since honest majority is there, so we can say that given a broadcast protocol, we will have a Byzantine agreement protocol. So last option is correct. So these three are the correct options basically. Okay. So this is all about the week 1 assignments. Now let's quickly understand the concepts of week 2 topics. So in week 2, basically we first discuss about the proof of validity and proof of consistency of the EIG protocol for perfectly secure Byzantine agreement with n greater than 3T. So how do you prove the validity and consistency property, right? So for that we have a couple of lemmas here. So just let's go through the lemmas quickly. First lemma says that if Pi, Pj, Pk are honest, right, then value of x, so x is the label or tag of a node, and I denotes that we are talking about value of node with label x in the EIG tree copy of party Pi. So this is value corresponding to the EIG tree of party Pi, and this is value corresponding to the EIG tree of party Pj, and value at node label x. So all the nodes with label that ends with some honest party ID, right? Pk is honest. So if a node label x that ends with a honest party ID, so such nodes will have the same value throughout all honest parties. That is what this lemma says. Now this is quite trivial to see. Why? Because if value x at EIG tree of party Pi is some value v, that means Pk must have sent to Pi the information that so let's denote x with this notation, some p1 till say pm, and then there is this so this is the label, right? Now pk, so x nodes, the label of node x ends with honest party ID pk, and that means, so let's write without loss of generality. There is some value, say p pc, let's say just the previous node. So this value will be assigned some value v by pi only if pk had conveyed the information that the node with label p1 to pc has the value v in round r. And since this is the case and pk is honest, it must have sent the identical information that the node with label p1 to pc has a value v to other honest party pj as well. So pj also assigns in its local copy of EIG tree, assigns the value v to the node, this value appended with the party ID k, right? Party ID k, right? So this value with this label will get the same value v at copy of other honest party pj also. So that's why lemma 1 is satisfied. Now we can also verify that for all labels 0 to t. So as you remember, the EIG tree has a total of t plus 2 labels. The root node level is 0 and the leaf node level is t plus 1. So leaf node does not have any children, but apart from that, all the other nodes who have level from 0 to t, every node at level L will have majority of child nodes whose label ends with the index of an honest party. This is true because as you know that at level L, a node has n minus L number of children, right? And the level L is actually upper bounded by the value t, right? L is belonging to 0 to t, so L can have maximum value t, or in other words we can write minus L is greater equal to minus t, which means n minus L is greater equal to n minus t. Also, among these n minus L children, at most t number of children can be ending with a corrupt party index. So the rest of the child nodes, that is n minus l minus t number of child nodes, are honest, and that value is actually greater than t. Why? Because from this step we can write, by subtracting t from both sides, we can write this, and this quantity n minus 2t is clearly greater than t, since we know that n is greater than 3t. So the number of honest child node, number of child node with ending with honest party id is greater than number of child nodes with ending with corrupted party id. So there will be majority of child nodes ending with honest party. So lemma 2 is satisfied. For lemma 3, if x ends with the index of an honest party, for every honest pi, new val x is equal to val x, that is before reassignment and after reassignment their value will be same, and that value will be v throughout all the honest parties, right? For every honest party this value v will be same. This also can be proved using the lemma 1, lemma 2 as well as a induction hypothesis, right? Using a induction proof where we can show that this is actually true. Now using all these three statements, actually the validity can be proven, because in validity we say that if the BA protocol starts with all the honest parties having the same input, in that case the output of BA protocol will be that value only, right? And with the application of these three lemma we can actually prove the validity property. For the consistency property we need to define two different terminologies. One is path covering and another is common node. So path covering is nothing but for a given tree, right? There are nodes going down. So path covering is nothing but a set of nodes that covers all the paths from root to leaf. That means you take any path from root to leaf, your set of nodes. So path covering is nothing but a set of nodes, and it covers all the paths from root to leaf. That means any path you take from the root to the leaf, to any leaf, at least one node in that path should be a part of this set. Then only we call this set to be a path covering. And another terminology is defined, which is common node. So a node is said to be common if all honest parties have same new value assigned to that node. So now basically there are two claims or two lemmas where they say that in EIG protocol there must exist a set of common nodes which also constitutes a path covering. Basically they will be nothing but the set of all the nodes that end with some honest parties index. By the property lemma 3, actually if any node that ends with, whose label ends with honest parties index, it will actually have the same value throughout all the honest parties, and they will constitute a path covering also, because otherwise we can show that some property will contradict basically. So, and then there is another lemma which says that if there is a common path covering of the subtree rooted at any node x, then x is common, and using this property we can finally show that the root node of the tree, which actually has a common path covering by lemma 4, will be a common node itself by the application of lemma 5, and then consistency property will be satisfied because these new values are consistent throughout all the honest parties, and they will be reflected upwards through the properties of path covering, and finally the root node of all the honest party will be assigned the same value using the bottom up approach of EIG protocol. So these parts are these proofs are actually discussed in detail in the lecture. So we will just move forward to these other topics, which are basically improvement of communication complexity from EIG protocols. So since in EIG protocol, at each round every party needs to send all the information of its local tree in the previous level to all other parties. So there is huge amount of information exchange at each round of the EIG protocol. Now we try to reduce that much communication complexity, and we design a efficient protocol which is called phase king protocol. Now there are two versions of phase king protocol. One is phase king 1 and another is phase king 2. In phase king 1 protocol, basically you get n greater than, so you assume n greater than 40. So the threshold restriction is a bit loose here. So you need to have lesser amount of corrupt parties to achieve the Byzantine agreement using phase king 1 protocol. Whereas in phase king 2 protocol, you again come back to the threshold scenario where maximum number of corrupt parties can be n by 3, right? So, and both the protocol has t plus 1 number of phases. In phase king 1 protocol, each phase has 2 rounds, whereas in phase king 2 protocols, each phase has 3 rounds. In both the cases, each phase has a designated king party. So king is nothing but kind of leader doing some extra operation than the other parties. So usually in the last round in phase king 1 protocol, the second round of each phase involves communication from the king party but from no other party, and in case of phase king 2 protocol, for each phase the third round involves communication from the king party only, right? Also the king party should be different for each of the phases. So you can notice that since there are t plus 1 phases and there can be at most t corruption, so among these t plus 1 distinct king parties throughout the t plus 1 phases, at least one honest party must be there chosen as the king of that phase. So among t plus 1 phase, at least one phase will be there where phase king is actually an honest party, because there can be at most t corruption, but we are running the protocol for t plus 1 phases, so one phase must have a honest king, okay? And both of the protocols achieves perfectly secure Byzantine agreement. So if we basically in the lecture, all the protocol description as well as the proof of validity and consistency along with the helping lemmas are worked out in detail. Here we will see a quick demonstration of phase king 1 protocol while recapitulating the protocol idea also. So the protocol description we will recapitulate on the way while demonstrating the protocol. So since we need n greater than 40, so I am taking t equal to 1 here and n equal to 5 here. Now we have the parties P1, P2, P3, P4 and P5, and let's assume their initial input to be like this, say 0, 0, 1, 1 and 0, and let's assume that P2 is the corrupt party here. Now what will be the, so how many phases will be there? T is 1, so there will be total 2 phases and each phase has 2 rounds. So let's 2 phases will be there, and let's say that phase 1 has king, phase 1 king is let's say P1, and phase 2 king is P2. Okay, so what happens, we will demonstrate. So phase 1 king is P1. What happens? So in round 1, if you remember, all the parties will broadcast their own bit. So we denote it as a preference bit, and at the beginning preference bit is initialized with their own input values. So in the beginning P1 has pref 1 equal to 0, P2 has pref 2 equal to 0, P3 has pref 3 equal to 1, P4 has pref 4 equal to 1, and P5 has pref 4 equal to 0. So in round 1 everyone broadcasts their own value. All the honest party will broadcast the identical value to everyone, but we cannot comment on the behavior of malicious party P2. So let's just write down this in form of a table. So here are the parties in form of receiver. So I am considering them as receiver, and from whom they are receiving. So in this direction I am considering them as sender. Okay, so P1 being a honest party will send the value 0 to everyone, right? There is no cheating there. P1 is a honest party, so it will broadcast the value 0 to everyone. P2 is a malicious party or corrupt party. It has input 0, but it may choose to send different inputs to different parties. So it will broadcast say 0, 0, 1, 1, 1. This is inconsistent because P2 is corrupt party. P3 is honest party, and it will send its input 1 to everyone. No cheating. For P4 also the input is 1, so it will send 1 to everyone, and P5 sends 0 to everyone. Okay, now send and receive is completed in round 1. Now what happens is that every party after receiving the values, right, now we look at the column. So P1 has received these values from n parties, so it will check what is the majority value that it receives, and it assigns a TMP bit. So let's write the TMP I. So what is the value of temporary variable 1? This is the majority of this received bit. So this is 0 for P1, for P2 it is 0, for P3 it is 1, for P4 it is 1, for P5 it is 1. If there would have no majority, then default value would have been assigned, that is some bot value would have been assigned, but here P1 gets 0, P2 gets 0, P3 gets 1, P4 gets 1, and P5 gets 1. That is the majority value, right? Okay. So TMPI bits are assigned for everyone, and remember that here king is P1. So in the next round, round 2 only has P1 as the only sender because it is the king, and everyone else receives the temp1 value, that is the temporary value of the king party, as So everyone will receive P1's TMP1 value in the round 2. So that value is 0, so everyone receives 0 from P1, and since P1 is honest, it will send the same value to everyone, no cheating, right? So everyone has received 0 from P1. Now what happens? Now everyone will check, every party will check whether the TMPI value of its own was received from more than n by 2 plus t parties. So here n by 2 plus t is nothing but 3, right? So if more than 3 parties were more than 3 copies of bit TMPI was received in round 1, right? So for P1, it received its own TMP value 0 3 times, but not more than 3 times, right? So it assigned to itself the value of TMP k, that is the TMP variable received from the king party is assigned to final pref bit. So let me write it as a row. So bit pref I for P1 becomes the TMP k value, that is 0. For P2 also, it received 0 for 3 times but not more than 3 times, so it will assign the value TMP k as its preference bit, so that is equal to 0 again. Using similar logic, P3 also assigns pref 3 equal to TMP k, that is 0. P4 also assigns pref 4 equal to TMP k, that is 0, and P5 also assigns the value 0. So you see that since P1 is a honest party, at the end of phase 1, so at the beginning of phase 1, the honest party P1, P3, P4, P5 had different set of inputs, but at the end of phase 1, where the king P1 is a honest party, everyone has reached a consensus. Every honest party has reached a consensus that all of them has value 0 as their preference bits. And once this consensus has achieved, this will be maintained throughout the rest of the phases. So we will quickly look at what happens at phase 2 with king P2, right? So again we start with round 1. Okay, so in round 1 again we will just so the round 1 begins with this preference bit, right? So remember, this is the preference bits for beginning of phase 2. These were the preference bit for beginning of phase 1, the initial bits, but for beginning of phase 2, these preference bits are the inputs. And first, each party broadcasts its own preference I to everyone. So let's write in this manner. So P1 has value 0 as pref 1, and it will broadcast the value 0 to everyone. P2 has value 0, however it is a product party, so it may decide to send different values to different parties. So let's say it sends 1, 0, 1, 0, 1, different values to different parties. P3 has value 0, so it will broadcast 0 only to everyone. P4 also has 0, it will broadcast 0. P5 also has 0, so it will broadcast 0 to everyone. Now, so this is the sender direction. Now what values P1 has received at the end of round 1? It has received as majority. So what is the assigned value of TMPI? TMPI is nothing but the majority of received values. So P1 has received 0, 1, 0, 0, 0, 0. So majority value is 0. So TMPI in the round 1 of phase 2 is 0 for P1. It is 0 for P2. It is 0 for P3. It is 0 for P4 and it is 0 for P5 as well. Okay, now round 1 is completed. All the parties have their own TMPI variable set. Now round 2 begins. In round 2, as you know, only king party broadcasts. No other party has to do anything. So P1, P2, P3, P4, P5, all of them act as receiver, and only P1 acts as only P2 acts as the sender, because P2 is the king in this phase. And remember, P2 is a corrupt party. So P2 actually has its TMP2 value, which is 0, but it may choose to send different values to different parties. So instead of sending 0 to everyone, it sends 0 to P1, 1 to itself, 1 to P3, 1 to P4 and 0 to P5. So this is just arbitrary assignment. Okay. Now what happens? Each party will check whether its own TMPI value was received more than n by 2 plus t times. So n by 2 plus t is 3. So P1 checks its own TMPI value, that is 0, if it was received for more than 3 times in the round 1. So yes, P1 received the value 0 4 times in round 1 and 4 is greater than 3. So that means 0, that is the value of TMPI for party 1 that had 4 copies received in round 1, which is greater than n by 2 plus 3. So the preference bit, right, preference bit of P1 will continue to remain 0. It does not care about the king party's broadcasted value. For P2 also the value 0 was received 5 times, right, which is clearly greater than 3. So again the broadcasted value from king party is ignored and the TMPI value is retained. For P3 also the value 0 was received 4 times, which is greater than 3. So king's value is ignored and 0 is the preference value in round 2. Same is the case for P4 as well as P5. So as you can see, in the round 2 of phase 2, where king was actually a corrupt party, but it could not be able to affect the preference bit value of the honest parties, because all the honest parties had received their own TMPI value sufficient number of copies in round 1. So at the beginning of phase 2, all the honest parties had the same input bit 0, and at the end of phase 2 also it retains the same value 0 throughout all the honest parties. So P1 outputs 0 as the output of phase king 1 protocol, P2 also outputs 0, P3 outputs 0, P4 outputs 0, P5 outputs 0, and all the honest party has consistent output. Although they started with different set of inputs, at the end of the Byzantine agreement protocol, as expected, all the honest party are agreeing upon same value, that is the value 0 as the output of the protocol. So this is about the demonstration of phase king 1 protocol, right. Now I will give a demonstration of phase king 2 protocol. The reason I am giving this demonstration is it helps in visualizing the protocol in hand. The visualization is more helpful than just looking at the algorithm of the protocol, right? It makes your concept more clear. That's why I am giving the demonstration of this protocol with small examples. So now we move forward to demonstration of Phase-King2 protocol. Now since this Phase-King2 protocol was designed to support a larger threshold, that is here n is greater than 3t. So we take n equal to 4 and t equal to 1. Again we have 4 parties, P1, P2, P3 and P4 at the beginning of protocol, and let's assume that P3 is the corrupt party here, and let's assume the initial inputs are 1, 0, 1, 1. Okay. Now t is 1, so there will be t plus 1, that is 2 phases, right? 2 phase, and each phase will have 3 rounds. Okay. So they start with preference I equal to their corresponding input bi. So pref 1 is 1 initially, pref 2 is 0 initially, pref 3 is 1 initially, and pref 4 is 1. So let's start the phase 1. Phase 1, round 1. So in round 1, all of the parties will broadcast their own preference bit to everyone, including itself. So similarly, I write the sender receiver table here. So these are the receivers, and we will note down what they receive from all other parties as sent. So P1 will send the value 1 to everyone. Because P1 is honest, it will send identically the value 1 to everyone. P2 is also honest, so it will broadcast its value 0 to everyone. P3 has its input 1, but it is a corrupt party, so it may choose to provide different versions to different parties. P4 is honest, so it will give identical message to everyone. So sending and receiving of round 1 is done. Now starts the round 2. In round 2, everyone checks whether the value received in round 1, some value has more than or at least n minus t copies of some value. If that is the case, then it will broadcast that value to everyone. So it is not necessary that in round 2 every party will broadcast something. In round 1, every party will necessarily broadcast their own preference value to everyone. So each party takes part as sender in round 1, but in round 2 it's not necessary that all the parties will be sender. Only some of them can be sender. And what is the condition to be a sender? That some value should be received more than n minus t times to be a sender in round 2. So these are the receivers again, and we will choose whether some party is going to be sender or not. So looking at P1, so what is n minus t? N minus t is 3, right? So we check whether P1 receives at least 3 number of copies for some value. So P1 has received 1011, so it has received 1 3 times. That means it is eligible to be a sender in round 2. So in round 2, P1 becomes sender and broadcasts the value or propose the value 1 to everyone. Since it is honest, it will identically send the value 1 to everyone. What about P2? So P2 also has received the value 1 from 3 different parties. So 3 copies are there. So P2 is also a potential sender and it will propose the value 1 to everyone, and since P2 is honest, it will send out the same value to everyone. What about P3? P3 does not receive any value for at least 3 times. It has 1 0 0 1. So that condition is not satisfied. So P3 does not send anything in round 2. P4 also, due to the same reason, does not send anything. So only P1 and P2 broadcast their proposed value to everyone. Now each party, after receiving the values, they will check whether they have received some value for more than t times, right? So P1 has received 1 2 times. So t is 1 here. So it has received the value 1 more than 1 time. So it will assign the value preference I to this received value, right, in round 2. So preference 1 is 1 at the end of round 2. For P2 also, it has received 1 twice, which is more than once. So it will also assign preference to the value 1. P3 also assigns the value 1 to pref 3, and similarly pref 4 is also 1. Now round 2 is completed. So note that in round 1 sending and receiving are done, but nothing is assigned to preference value. But in round 2, some of the party choose to be sender depending on whether it receives some value at least n-3 times, and once this sending and receiving is completed, depending on whether a party receives some value more than t times, the pref I bit gets updated. So no assignment is here in round 1, but round 2 has some assignment for each party, right? However, it can be the case that for some party the condition that more than t times some value is received, that may not be satisfied. So it can be the case that the pref I bit is not updated in round 2 for some party. That may also be the case. But here in this example that we are working with, all the parties has updated the value pref I at the end of round 2. Now begins round 3, and since this is the final round for phase 1, only the king party will be the sender and others are the receiver. So apart from the king party, no one takes part as sender in round 3. So I am again writing P1, P2, P3, P4 who works as receiver, and let's assume, so I have not written it previously, so there are 2 phases, and let's assume that for phase 1 king is say the corrupt party P3 is the king for phase 1, and for phase 2 P4 is the king. Just without loss of generality, this is the assumption. So if P3 is the king party in phase 1, so P3 only broadcasts its preference bit to everyone. Now note that P3 is a coded party, so it may deviate from the protocol, and instead of sending the actual preference bit 1, it can choose arbitrary values to all the parties. Okay. Or maybe just anything it can send basically. Now each party will check that whether the preference I bit, right, what they assigned in round 2, that bit was received from at least n minus t parties during round 2. So n minus t is 3. So now the check is that whether P1 checks whether its pref1 bit, that is 1, was received from at least 3 parties in round 2. But we can see that only 2 copies of 1 were received by P1 in round 2, not 3. So if condition is not satisfied, now else part says that in that case update pref I equal to pref k, that is the preference bit of king party, whatever is received in round 3. With that you will update your preference value. So during round 3 pref 1 bit for P1 is equal to pref 3, that is the king party. So king party has sent 1 to P1, right, as the pref k. So P1 updates its pref 1 to be 1. In case of P2, so P2 also had its preference 2 bit 1, but 1 was received only from 2 parties, not n minus t, that is 3 parties. So it will also update its pref I bit according to the bit received from king party. So king party told P2 that my preference I bit is 0. So P2 accordingly updates its pref 2 bit as 0. In case of P3 also, it had its pref I value 1, but it was not received from 3 parties, it was received from only 2 parties. So it updates the value with the value received from king party P3, which is 0. Same is the case for P4. So pref 4 is assigned to be 0 at the end of round 3 of phase 1. So this phase is completed. Now we start the next phase, phase 2, with the preference bit of individual parties as 1 0 0 0. And in this phase P4, the honest party is going to be the phase king. Okay, now round 1 of phase 2 is started. So P1, P2, P3 and P4 act as receiver, and they will receive the broadcasted value from each of the parties, right? So round 1 is just the broadcast by each party of their own preference bit. So just sending and receiving happens here. So P1 has preference bit 1, so it will broadcast the value 1 to everyone. P2 has value 0 and it is honest, so it will broadcast the value 0 to everyone. P3 has value 0, but it is a corrupt party, so it may send completely arbitrary value to everyone. P4 has value 0 and it is honest, so it will send 0 to everyone. Now round 1 is completed. In round 2, only some of the party can be sender, depending on if it has received at least n minus t copies of some value in the previous round. So let's check whether P1 is a valid sender for round 2. So P1 has received 1010. So no value has been received for 3 times. N minus t is 3. So no value has been received by P1 for 3 times. So P1 is not a valid sender here. What about P2? P2 also has received 1010. So it has not received any value for 3 times. P2 is also not a valid sender, and with the same logic we can see neither P3 nor P4 is a valid sender. So none of P1, P2, P3, P4 qualifies as a valid sender to propose some bit to anyone. So no one basically proposes anything in round 2. At the end of round 2, basically the pref I bit of each party would have been updated according to the received value in round 2 if some value would arrived and some particular condition would have been satisfied. But since nothing happens here in round 2, so pref I bits remains unchanged as the initial. So initial was 1 0 0 0 with the value they started phase 2, so that remains unchanged. Now starts round 3. What happens now? Only the king party is the sender, right? So king party here is P4, so P4 will send its own preference bit to everyone, and its own preference bit is 0, right? P4's preference bit is 0, so it will send 0 to everyone. Now each party checks if its own bit pref I was received more than n minus t times in the round 2. But remember, in round 2 no one received anything from any party, so basically that if condition will fail for all the parties here, so they will directly jump to the else condition where it is said that pref I is updated with the pref k value, that is the preference bit of the king party. So P1 will update its preference bit with the preference bit of the king party that it receives, so that will be 0 0 0 0. Everyone ignores the if condition of round 3 and there jumps to the else condition where pref I bit is updated with the pref k, which is 0 for everyone. Since P4 is honest, it sent 0 to all the parties and all the parties updates pref I to 0, and that is the end of the protocol. So at the end of the round, at the end of phase 2, you can see that all the honest parties P1, P2 and P4, they are agreeing upon a common output value which is 0. So this is a successfully executed phase king 2 protocol. Okay, so I hope this helps you visualize the phase king 2 protocol better, and all the proofs related to Byzantine related to the validity and consistency property of phase king 2 protocol is discussed in detail in the lectures. Now the next topic of this week was the Turpin cone domain extension protocol. So we can just visualize it through a demonstration. So let's start with n equal to 4 and t equal to 1, and let's say underlying BA protocol. So domain extension is nothing but how to run Byzantine agreement protocol for bit string instead of bit. So till this point, whatever protocol we have seen for perfectly secure Byzantine agreement, they are EIG protocol, phase king 1 protocol and phase king 2 protocol. All of them were bit agreement protocol, that is all the input party are starting with some binary bit, and at the end of the protocol all the honest party agree upon a consistent bit output. But what if each of the parties start with not a bit but with a bit string, say of length L? Okay, so each party has L bit length input at the beginning of the protocol, and we want the consistency and validity to be maintained at the end of the protocol for all these L bits. Okay, then how do so that is what we call domain extension, and we have the Turpin cone domain extension protocol described here. quick demonstration of this protocol. So let's say L equal to 3. Okay. Now, so this domain extension protocol actually will run in R plus 2 rounds, where R is nothing but the number of rounds required for running the underlying Byzantine equivalent protocol. Okay. So if we are considering phase king 2 protocol, then the required number of round is T plus 1. So that is the required number of phase, right? So there are 2 phases to run the phase king 2 protocol, and apart from that 2 extra rounds will be required. So if we talk about round in phase king 2, there will be 2 phases each containing 3 rounds, which makes total 6 rounds, and for these extra 2 rounds, that will make it total 8 rounds of the protocol. So we will just see the first 2 rounds of the protocol, and we just replace the whole 6 rounds of phase king 2 as a black box and deal with the output. Okay. So let us say that we have P1, P2, P3, P4, where P2 is corrupted, and let's say P1 has initial input 101. So let's say all the honest parties are starting with the same input, and corrupt party can have any input initially. What we expect is that at the end of the protocol, all the honest party will continue to have this string 101 only. Okay. Now, so the first round is that. So let's start with round 1. Here everyone will broadcast their own initial input to everyone. So again, let's write it in receiver, and this is as sender. So P1 is a honest party, and it has the initial input string 101, so it will send 101 to everyone. All the L bits are communicated to all the parties. What about P2? It can send basically anything, whatever it wants. What about P3? Honest party, so sends 101 to everyone. P4 also honest, so it sends 101 to everyone. Okay. So this round 1 communication is done. Now each party will check that if some value has been received at least n minus t times. Okay. If that is the case, they will assign it to some value yi. Okay. So in case of P1 has received 101, 001, 101, 101. So 101 has been received 3 times here. So it will assign to yi the value 101. Okay. Similarly, for the case of P2, it has received 101 4 times, so it will assign to yi the value 101. P3 also assigns 101 to y3, and P4 assigns 101 to y4. That is the end of round 1. What happens in round 2? In round 2, everyone will send their own yi to everyone. Now note that in round 1, it is not necessary that some pi will have a non-bot value. So in case, let's say here everyone has received 101 at least n minus t times, but if that would not have been the case, some pi does not receive some value v for n minus t times, in that case it would assign the value bought to yi. Okay. Now in round 2, everyone will send their own yi to everyone. So again, P1, P2, P3, P4 are there, and right, so this is as receiver, they work as sender. Okay, so yi for P1 is 101, so it will honestly broadcast the value of yi to everyone. P2 also have 101, however it is scored party, so its behavior is unpredictable, so it can just randomly send values to everyone. P3 has 101, so this is correctly sent to everyone, and same is the case for P4. Now what happens? Now every party again checks that whether some y value is received at least n minus t times, that is 3 times. So again P1 has received 101 4 times. So yes, it has actually received more than 3 times. So it will send its corresponding vote bit, which is a single bit, to 1, and also it sets its corresponding zi value to the maximum received non-bot value, which is 101. So zi value is 1 and vote I value is 1 for P1. What about P2? P2 also receives 101 thrice, so it updates its vote I to be 1 and zi to be 101. Same is the case for P3 and P4. Okay. Now at the end of round 2, basically a Byzantine agreement protocol, let's say Hesking 2 protocol, will be run among P1, P2, P3 and P4 with bit input as their vote I input. So they run the Hesking protocol with corresponding vote variables, and since all the honest parties has same input at the beginning of Hesking 2 protocol or any Byzantine agreement protocol they might have run as black box, at the end of the Byzantine protocol, due to the validity property, all the honest party will have same output, is the 1. Okay. Since P1, P3, P4, so we do not care about the output of P2, it can be anything. Okay, it can be 0 or anything, we do not really care about that, but our point of interest is that P1, P3, P4, due to the validity of the underlying Byzantine agreement protocol, which runs in 6 rounds for Hesking 2, after that everyone has received their bit output to be 1. Now if the Byzantine agreement protocol output is 1 and also each party has some non-bot zi value assigned to it, then they will output their corresponding zi value as the output of extended domain Tarpin-Cohn protocol. So PI has Byzantine agreement output protocol, Byzantine agreement protocol output 1 and zi 101, so its final output is 101. We do not care about P2. P3 is a honest party, its BA protocol output is 1 and its ZI value was a non-baud value 101, so its final output is 101, and same is the case for P4. So we can see that as expected, so all the honest parties started the protocol with individual 3-bit length input 101 and they have output 101 only at the end of the 8 rounds, considering phase king 2 to be the underlying BA protocol. So this is the final output achieved. Okay, so that is how we practically demonstrate the type-in cone domain extension protocol. I hope this example become helpful for you to better understand the protocols and all the other details regarding the proof of consistency, proof of validity. They are discussed in detail in the lecture and they completely relies on the validity and consistency property of the underlying BA protocol. Okay, so please refer to lecture for the detailed proofs, and that's it for this week. Okay, so I will end here, and in next week tutorial session, that is basically tomorrow, we will discuss the assignment for week 2 and we will also discuss the concepts of week 3 contents. Okay, so thank you for listening.